The Standard Model contains 12 fundamental fermions, but their masses are far from uniform. They are scattered across a wide spectrum that defies simple explanation. This chart arrays 12 particles along a logarithmic scale spanning 12 orders of magnitude. The Higgs mechanism explains how they acquire mass, but cannot predict specific values. Thus, every single mass must be measured experimentally and inserted into the Standard Model by hand. This reliance on manual inputs suggests the mass hierarchy is a result of structural constraints within the space particles occupy, rather than a dynamical process. This is the three-sphere quotiented by the binary icosahedral group, the topological base space for a new mass derivation. We begin with a single postulate. The boundary of a Mobius strip embeds into this closed manifold, with no adjusted data. Within this geometry, we separate a particle's identity, its quantum numbers, from its mass, or its energy scale. Particle identities emerge as rigid projections of icosahedral subgroups, while their masses are the direct numerical outputs of the resulting spectral geometry. The binary icosahedral group contains 3 rigid stabilizer subgroups inherited from the icosahedron, its faces, edges, and vertices. The face stabilizer, Z3, is an order 3 subgroup. Restricting a propagating mode to this face geometry splits it into 2 distinct channels, color singlets for leptons and colored triplets for quarks. The edge stabilizer, Z4, has an order of 4. This edge geometry enforces the spin statistics connection. It assigns complex pairs to a domain of 120 for half-integer spin and real content to a domain of 60 for integer spin. The vertex stabilizer, Z5, is order 5. Galois conjugation at these vertices distinguishes between 2 non-trivial vacua, creating the mathematical foundation for the electroweak interaction. Color, spin domain, and electroweak identity are inescapable requirements of the 2I geometry. These symmetries generate the specific slots the particles must occupy. The Coxeter-Galois gate acts as a structural filter, locking in the weak isospin for each geometric slot. Stage 1 filters by parity. If a mode enters the spectrum with an integer parity, it is restricted to the bosonic channel, receiving an isospin of -1/2. Stage 2 handles half-integer cases by checking if the 13-17 Coxeter-Galois conjugate pair is mathematically stripped by the vacuum. If that pair is stripped and the tensor product contains Galois-Mon fixed content, the isospin is -1/2. If these conditions aren't met, it is +1/2. This is followed by the Dirac-Eta sign gate, which links parity directly to electric charge. Positive electric charge in this model mathematically requires a negative eta value. By closing the circuit with the Gell-Mann-Nishijima formula, every fundamental quantum property is perfectly locked by the topology before mass is ever calculated. The master mass formula is composed of 4 factors, all derived independently of Standard Model data. First is the vacuum energy floor, which sets the absolute mass scale. This is the 4th root of the cosmological constant energy density, roughly 2.25 milli-electron volts. The second factor is the costant sunflower phase, which encodes a representation's position on the domain grid. The third factor, the McKay elevator, is an exponent that drives the 12 order of magnitude spread from the vacuum floor. Finally, Reidemeister torsion generates the fine structure within each individual mass shell. Integer spin AirReps produce exact algebraic closed forms, while half-integer AirReps produce finite sums of L-function derivatives. Combining these factors yields precise, inevitable mass values, derived purely from the manifold. The geometry outputs 24 ranked entries. When compared to measured data, the alignment is striking. We use the electron at rank 12 as a benchmark, anchoring the mass scale. With the scale anchored, 6 of the remaining 8 charged fermions land within a factor of 3 of the topological entries. Rank 15 sits at 103 mega-electron volts, directly between the muon and the strange quark. The phase decomposition separates this shell into a singlet component for the muon and a colored component for the strange quark. A cluster of entries between ranks 18 and 22 aligns with the known mass of the bottom quark. Instead of being random, the previously chaotic spread of particle masses has now been mapped to a rigid, mathematically fixed set of coordinates. The model still faces unresolved tensions, such as the mass of the down quark and the gap where the second neutrino mass should sit. There is also a dead zone between ranks 4 and 9. This mass range, spanning from electron volts to kilo-electron volts, is an experimental void where no fundamental fermions have been observed. These entries are either propagating states awaiting discovery by sterile neutrino searches, or they are non-physical residuals of the manifold's topology. This framework is an exact mathematical comparison rather than a dynamical prediction of physical behavior. The topology dictates the identities and the mass plots, while observational data confirms which generation occupies which mathematical entry. The success of these matches suggests the standard model is a rigid reflection of this underlying geometric truth.